We all hear how much our carbon footprint is impacting global warming. Flights being a major factor of this, but they're really hard to avoid in this day and age. My family in Spain have to travel for work, and in many cases, flying is the only reasonable option.
But it's not just you. There are so many things at play. Transporting cargo, you need to move medication and food around the planet, and there's also a huge economic benefit to aviation. You've got jobs that are created, but then also tourism is the number one industry in a lot of different countries.
So we can't eliminate it. Really, we don't want to. So how do we go about reducing its impact?
There's a global call to reduce aviation emissions, and we can do this in 3 different ways. By using less fuel, by using a carbon neutral fuel, and by using a zero carbon fuel.
Less fuel refers to all the work going into making current engines more efficient, so they use less fuel. In the same way that modern cars can get us a lot further on a full tank than they did decades ago.
Exactly. And then there's carbon neutral methods, like sustainable aviation fuels, which recycle the carbon and emit no new carbon into the environment.
Then instead of just reducing emissions, we can eliminate them altogether in 2 main ways. The first is batteries, and the other one is hydrogen.
Now, batteries are an interesting idea, as we're all probably thinking you've got electric cars, so it's hard to imagine that a battery-powered plane could get us somewhere as far afield as Italy, for example. And as it stands, the technology can't. Batteries are heavy, so for aviation, it's far more suitable for very short city-hopping flights.
So hydrogen is our best option, because it is zero carbon at the time of flight. But it comes with a lot of challenges. It is notoriously combustible and difficult to store. To keep it in a small space, it has to be stored at extremely low temperatures, and it can be quite challenging on the materials being used.
And we've not even mentioned the lack of supply chain and airport infrastructure. So this is a particularly challenging fuel that we're talking about using for the commercial aviation industry. On the other hand, we have been using hydrogen for spaceflight for the past 60 years.
This means, however, there's actually a huge opportunity for us to improve our understanding. And that's being done now, as we speak.
As you will have seen in the news, there are a number of companies who are proving that this is a possibility, which means that we have a great opportunity to completely redesign aircraft as we know them.
But there's still a lot we need to understand better, especially since aviation is one of the most regulated industries. So in order for us to ever fly on a hydrogen plane, it will have to pass through loads of tests and prove that it's safe.
But this research requires public funding and a lot of expertise to help us reach this common goal.
This is something we can only achieve through the power of collaboration.
Yes, and the Oxford Thermofluid Institute is hosting a program funded by a branch of the UK Research Institute called Making Hydrogen Work in Zero Carbon Jet Engines. This program brings together 30 people across 10 disciplines and 3 universities: Oxford, Loughborough, and Imperial.
This program aims to provide the aero industry with the research that it needs to switch aviation fuels with hydrogen. It looks at the whole system, from fuel tank to engine. In order for us to dive into some of the research we're working on, let's look at how a hydrogen plane would work.
So, on aircraft, space is limited, and we need to be really mindful of weight in order to make sure it can get off the ground. Now, hydrogen at room temperature is a gas, but in order for us to store it on an aircraft, we need it to be in its liquid form. Let's take water as an example. If we imagine a cloud of steam, in order for us to condense it, turn it back into a liquid, we need to reduce its temperature. And for hydrogen, this is no different. But hydrogen needs to be reduced to below minus 250 degrees centigrade, and a lot of energy is required in order to make sure it doesn't turn back into a gas and boil off.
To then move the liquid around the plane, centrifugal pumps are used. This is where my work comes in. These devices take the liquid in and spin it outwards, a bit like how your washing machine spins water around away from the center. That spinning raises the pressure of the liquid and moves it where it needs to go. Hydrogen is tricky. Because it is the lightest fuel we know, there is very little mass to push outwards, and so very little pressure builds up. To compensate, the pump has to spin incredibly fast. and we're talking about speeds beyond anything used in the aviation industry today. And this brings us to another problem. Liquid hydrogen, as we've said, is quite close to boiling, which means that it's very likely that bubbles will appear inside the machine. Bubbles are bad news for pumps. They reduce its efficiency, and over time, they physically ruin the pump.
Basic.
So this means that hydrogen pumps are unlike any other we're used to making. So we have to completely rethink their design. As you can imagine, it is both difficult and expensive to do experiments on every test design. At the Oxford Thermofluid Institute, we build computer models. They're like a virtual transparent pump that allows you to see what the flow looks like inside the machine and predict where these bubbles will appear. This work is vital because it allows us to test ideas faster and design pumps that will move liquid hydrogen around both safely and effectively.
In order to move the hydrogen to where it needs to go in the aircraft, we rely on pipes. And these pipes are often made of materials that are prone to a phenomena called hydrogen embrittlement. This is a type of damage that turns normally strong materials, especially metals like steel, unexpectedly brittle and prone to cracking. Hydrogen atoms are very small, and this this means that they can slip inside the material, and which can happen oftentimes during manufacturing and corrosion. And it can make normally strong materials break, sometimes unexpectedly.
So we don't know what hydrogen embrittlement is, but how do we safely study where the hydrogen slips into the metal? And more importantly, how do we stop it? With this program, our colleagues are looking exactly at that. They use computer simulations to watch hydrogen embrittlement happen in slow motion. They can model a small sheet of paper being pulled apart while in contact with hydrogen. Metal. If I imagine taking a sheet of paper and I pull it to tear it, it's a bit awkward. If I make a patch on the side and I pull it, it will tear instantly. All my pulling force is concentrated at that castwheel. When you zoom into a metal, at a microscopic level, there's always small imperfections. And like the cut in the piece of paper, at this point is where the stress concentrates. And here's the critical part. At those points where stress is high is exactly where the hydrogen builds up. So adding hydrogen to these already weak points is how embrittlement happens. But by understanding where the hydrogen goes, we can design materials that keep it away from those weak points and are tougher when faced with hydrogen for long periods of time.
So, the hydrogen has traveled from the tank through the aircraft in pipes and has made its way to the jet engine, and more specifically, the combustion system. Now, this is where my research comes into play. At Loughborough University, in the National Centre for Combustion and Aerothermal Technology, or NCAT, we're focused on advancing combustion systems in order to help the aviation industry achieve its net zero targets. At the facility, we have the ability to conduct experiments using hydrogen in order for us to better understand the combustion process. Now, as a combustion engineer, one of the best properties of hydrogen is how easy it is to light. But this is something that we're not used to with jet fuel. Let's imagine for a second I had a bucket of jet fuel sat in front of me full to the brim. I lit a match and I dropped it in. Nothing would happen. In fact, the match would get extinguished by the fuel itself. Hydrogen is completely different. It's highly flammable, but that means that we have a really great opportunity to redesign the combustion system. Now, since we understand that hydrogen is so easy to burn, controlling it and using it efficiently is really important. That's why at NCAT, we're going to be investigating the operability of the combustion system. What do I mean by operability? Well, in basic terms, it's the ability for a system to respond through a range of conditions. Think takeoff and cruising up at altitude. These have two completely different requirements. If we imagine you're on a roundabout pulling off onto a 70-mile-an-hour road, your foot's flat on the ground and you can feel the engine working really hard, right? That's no different to what's happening in a jet engine. Once you hit 70, you can lift your foot off and you can feel the engine has to work a lot less hard to keep you there. Now, for a hydrogen plane, this process is no different. But we need to make sure that the combustion process is as efficient and effective at takeoff as it is cruising at altitude. And the work we're doing at Loughborough will help us ensure that.
Isn't this exciting? Enabling this collaborative research is a great way to get a critical mass of talent tackling this problem. And most importantly, it's key that the UK remains at the forefront of research into aviation.
We have a lot of researchers who are coming together to achieve this common goal. And with that, to go back to the question that we posed in the title of our talk, flying into the future, can hydrogen get us there? We think so. Thank you very much for coming with me.